Yeah, oxidation and reduction reactions. Okay, this is a pretty fun topic. It puts a little bit of a different spin on some of the chemical reactions that we've talked about in class so far. You may have heard of oxidation and reduction. If you have, that's great. Let's talk about what this is. So, an oxidation or reduction reaction is one where electrons are transferred from place to place within the reaction and the oxidation numbers of elements change. And that is really important because we have not talked about the idea that oxidation states of different elements can change over the course of a reaction. And let me tell you what I mean by that, just so we're on the same page. So here's a reaction that we're pretty familiar with. We're going to work with this one a lot in this video. We have the synthesis of iron oxide from iron and oxygen gas. And so in the past, what we would have thought here is that, okay, we know that oxidations, the oxygen's oxidation number here is -2. That's pretty normal for us, and we must have gotten that 3 from the idea that this is a +3 or type 3 iron ion, right? Which means that, we would have thought, well, this must be then type 3 iron that goes through this reaction to make this compound over here. The reality is not quite that simple, and it's a great way to learn this stuff initially. But now we got to get a little more in depth about what these oxidation numbers really mean. Just as a review of oxidation numbers, they are the number that results from atoms gaining or losing electrons. And so remember that positive oxidation states mean that atoms have lost electrons, so that their proton number is greater than their electron number in the amount of that positive oxidation state. And for a negative number, that means that the atom has gained a certain number of electrons, so that its electron count is this many more than the protons that are present in the atom. So hopefully that's enough review on what an oxidation number is. And yeah, they can change, and that's the first we're hearing of this, okay? So let's talk about oxidation rules here for a few minutes. Some of this will be new, and some of this will be stuff that you already know. But the biggest one that is new to you is that the oxidation state of a free element is 0. And what I mean by a free element is, like in this reaction here, iron is a free element. It's not connected in a compound, so it cannot have a +3 oxidation state. In reality, its oxidation state is 0. Oh boy. So what that means is that we've got some new stuff to take into account here. Okay, so anything that's not in a compound has an oxidation state of 0. All right. Diatomic gases like the oxygen molecule that you see here, they also have an oxidation state of 0, and that includes all diatomic gases, hydrogen gas, nitrogen gas, fluorine, and so on. Hydrogen is almost always a +1, and that's pretty normal for us. We think of hydrogen's oxidation state as +1. It generally loses its 1 electron to become a +1 ion, and that's something that we've worked with before. But it's almost always a +1. If it is bonded to something that is more electronegative than itself, then it's actually going to be a -1. So we don't see that too often, but it can. Like an example of that might be something like calcium hydride. If we have calcium CaH2, the hydrogen's oxidation state in this compound is a -1 instead of a +1, and that's because it's actually gained electrons instead of losing them. Anyway, and then these two are pretty similar to things we know already. The group 1 elements on the far left of the periodic table, these guys here are always +1. The group 2, they're +2, and that's pretty usual. We lose that many electrons from the atom. And then oxygen's oxidation state is almost always -2. This is a really, really grounding rule for us moving into this oxidation and reduction stuff. It can have a different oxidation state if it's part of a what we call a peroxide compound, but we're not going to see that in our course. So for all intents and purposes, just consider that oxygen is always a -2. It will be for any examples we do in class or any practice work. Okay, so assigning oxidation states is pretty easy once you know how to follow these rules. Okay, so let's talk redox here. So this term redox, that's just kind of a shorthand abbreviation of saying oxidation and reduction. See, reduction, oxidation. It just means that one element is oxidized, and the term oxidized means that the oxidation number of the element increases. It goes up, okay? So like, for example, it could go from a +1 to a +2, or a 0 to a +1, or something like that. It goes up. And then the other element in the reaction is reduced, which means that its oxidation number decreases. So, we could go from a 0 to a -1, or a +2 to a +1. It just, the number goes down, and that element has been reduced, okay? Interesting, easy way to remember this is this little saying. I learned this in high school, actually. Leo says grr. Leo is, we think of Leo the lion, and grr might be like a sound that a lion makes. So this just stands for a couple things. Losing electrons is oxidation, okay? And then gaining electrons is reduction. Gaining electrons, reduction. There's a couple other little mnemonic devices that can help you out, but I think this one is the best one I know. Okay, so let's do some examples of some reactions and see what is a typical redox reaction. So here's our iron oxide example again. Let's figure out how to determine which element is oxidized and which element is reduced. Okay, so the first thing you do in a setting like this is to assign oxidation numbers to all of the elements in the compound, okay? If you have a polyatomic ion in your formula, then you can just assign the normal charge that you would to the polyatomic ion. We don't have an example like that here. So iron is a free element, so its oxidation state is 0, okay? Oxygen gas is a diatomic gas. Its oxidation state is 0. But now as they combine, we see that electrons are going to be transferred from one place to another to make this compound. So this is where we can determine what has been oxidized and what has been reduced. So we go back to our rules, and we remember this most grounding rule here is that oxygen's oxidation state is really always -2, okay? So we can assume that the oxidation number for oxygen is a -2. Now we know that the oxidation numbers have to sum up to a neutral compound, and so the -2, and if we have 3 of those ions, we have a -6 that we need to account for as a +6 over here for the iron. And that means that the oxidation state of iron has to be a +3, okay? So now we can determine that iron has gone from a 0 to a +3. So has its oxidation number increased or decreased? It's clearly increased. And what does the increase of an oxidation number mean? Well, remember this one, Leo says grr. So when you lose your electrons, then you have been oxidized, right? So iron is oxidized. Okay, and then let's look at the oxygen, which is going to be the one that's reduced. So oxygen had a oxidation state of 0, and its new oxidation state as a product is -2. You know, 0 is a pretty low number, but -2 is even lower, so it has been reduced. And so, yeah, it's been reduced. Okay, so iron oxidized, oxygen reduced. Okay, let's do another couple of these actually. So let's look at sodium oxide decomposing into sodium and oxygen gas. So here again, with our most grounding rule of oxygen being a -2, that means that, the -2 has to be canceled by a +2. We have that +2 to distribute over 2 ions, which means sodium is a +1. Also, we could have followed that rule of saying that the group 1 elements always have a +1 oxidation state. So anyway, that's kind of how we always know how to do that. And then over here, sodium is a free element, and oxygen gas is a diatomic gas with 0. So let's see who's been reduced. Sodium goes from a +1 to a 0, so we've gone down in number. This has been reduced. Okay, oxygen has gone from a -2 to a 0. He's worked his way up to a 0, so he's been oxidized. Okay, so even though 0 is a pretty low number, you know, -2 is even lower than 0, so it climbs up, it increases up to a 0. Okay. And then one more here. This is a good example because it's a little bit more complicated reaction. We can still do all this. So let's go ahead and figure all these guys out here. So we need to assign our oxidation state. So our negative, our group 17 elements are usually a -1, which means this must be tin type 2. Okay. So that makes a neutral compound. Here's our -1 on the chlorine again. It's a group 17 ion, so that means it's a -1. So the -3 has to be canceled out by a +3 on that iron. Over here, chlorine again, -1, which means that to be spread to multiply the -1 by 4 ions, that's -4 that has to be then canceled out by this single tin ion. So this is actually a tin type 4 ion. And then over here, chlorine is a -1 again. The -2 has to be canceled by a +2, so iron is type 2 over here. Okay, so now let's take a look at who's been reduced and who's been oxidized. Let's just start with tin here. So tin starts off as a +2 and it ends at a +4. So we've gone up in number. That means that it has been oxidized. Okay, chlorine starts as a -1. And look at that, it doesn't change. It's still a -1 as a product, okay? So when an ion doesn't change its oxidation state, we call it a spectator ion. And that's a term that you may remember from our solution chemistry unit, but this is a little bit different. Well, I mean, it's kind of the same idea. Nothing about it really changes. But in this case, it doesn't have to do with solubility, it just has to do with oxidation state. And then let's look at then iron, our last of our elements here. So the iron starts out as a +3 and it drops to a +2. Okay, so that means that iron has lowered its oxidation state, so it has been reduced. Okay, so that's how that works. You just sort of track what happens to the oxidation state throughout the reaction and, you know, assign those oxidation states correctly, and it shouldn't be too bad. Okay, so that brings us into the next part of this, which is something that you'll also see, and it's known as a half reaction. Okay, so here we have, one second here. Okay, so for a half reaction, what we want to do is basically write out the transfer of electrons as they occur in the reaction. So we have an oxidation half and we have a reduction half. Okay, let's start with our oxidation half here again. So here, remember, we had a 0, a +3, and a -2. Okay, so we need to look, this is where the balanced equation comes into play, because we really do have to account for the number of ions that are present based on the coefficients in the balanced equation. So the oxidation half has to do with the iron, because remember that iron has been oxidized in this reaction. So the oxidation half of the reaction is based on iron. So let's look at how iron changes. So here we have 4 iron atoms, really, because the oxidation state is 0. Okay, what happens over the course of the reaction is that we have now 2 iron, and then we have a total of 12 electrons that are transferred. Okay, and that's how you write the 12 electrons that are transferred. So remember that the 12 comes from the idea that we have a +3 oxidation state on this product iron, and if we have 2 ions of iron, each at +3, that's a +6, and then we have to account for the 2 coefficient here, so the 6 times 2 is what gives you the 12. And so really we're just accounting for the electrons that have been transferred away from iron. And the oxidation state, remember that oxygen in this example was reduced, and so our reduction half has to do with the oxygen. And so here we have our 3O2, and that has an oxidation state of 0. Here on this one, we're going to put the electrons on this side of the arrow, and that results in the coefficient 2 next to the oxygen part of the compound with its oxidation state. Okay, so basically what we're saying is that oxygen, 6 oxygen atoms, each pick up 2 electrons. Those are the 12. So the 6 times the 2 electrons each gives us our 12 electrons, resulting in this 2 oxygen with the -2 up here. So we have oxidation halves and reduction halves, and that just shows you basically the transfer of the electrons. Okay. So then these terms come up, the oxidizing agent, and these are terms that you'll see from time to time. The oxidizing agent is the element that takes the electrons. It's the element that gets reduced, and so it's a little bit confusing, feeling like the thing that gets reduced is the oxidizing agent. But what I like to think of electronegativity when I think of the oxidizing agent. Oxygen is like pretty much the most electronegative element right next to fluorine, and it has it's really highly electronegative, which means it really wants to take electrons. So we're kind of paying homage to oxygen by calling something the oxidizing agent. It's the thing that takes electrons to become reduced, if that makes sense. And then the reducing agent is just the opposite of that. It's the element that gives away the electrons. So the reducer is sometimes called the reducing agent. It is the element that gets oxidized, so it's the one that gives up the electrons. Okay, so that is oxidation and reduction, and I hope that helps.